All right. Good morning, folks. Well, hopefully, let's hope that the video is going to hold out and the computer is going to be working. Let me go ahead and start the time here, folks. Let me go ahead and share my screen here with you, and let's pick up exactly where we left off with yesterday. Go ahead and share this with you. Okay, let me see here. Okay, so hopefully you can see this. Let me try this one more time. Sorry, folks. Oh, no. Oops, sorry. Oh, yes. Oh, well. Okay, I'm sorry. I erased that. Oh, yes. Picture that we had. All right, let's try this again. So we left off with number 6 in your problem set, and I'm not going to draw the whole thing again, but hopefully at the beginning of the lesson you were able to see that. But we had then an object that's being tossed off of a cliff or an elevated platform. That's how you want to think about it. We said then that when you toss an object off the elevated platform, essentially what we have then is an object that is moving in a projectile manner. So it is projectile motion, and you want to make sure you keep that in mind. But all we're doing is we're looking at then the downward trajectory of the object. Okay, so we're looking at the downward trajectory. We are ignoring the upward trajectory of the projectile motion itself. So we're only looking at the second half of the motion as well. So in this particular problem then, we had an object that was being tossed off of a cliff. We were told then that cliff is off the ground. So remember what we have here, what I've drawn here for us is the surface. So this is the surface of the earth right here. Okay. So this is the surface of the earth. Okay. And we are elevating our platform here. So this is our cliff. So we're elevating the platform up above that surface of the earth at a distance of 78.4 meters. So this is 78.4 meters above the surface of the earth. So we have that distance there. So our object here is being tossed off of the surface of the earth. Okay, we're going to toss it off here. So there is our stone. And we initially throw it with a velocity, and we're told her that it is strictly a horizontal velocity of 5 meters per second. So the initial velocity here is 5 meters per second. And like I told you yesterday, like we talked about yesterday, the initial velocity here will only allow the x. So therefore, this initial velocity is horizontal. Okay? And so therefore, the vertical component of this is going to be 0. So therefore, there is the object here, if you can imagine this, as being tossing an object at the very top part of the parabola. Okay? So remember, at the very height of the parabola there is no vertical velocity. It's no longer moving up and it has not yet started moving down. So the vertical velocity, that is the velocity on the y, is going to be 0. So that's how we want to treat this here. We're treating this as if this were at the very top of the pathway and we're starting from there. And we are starting from there, we're elevating from there. And so therefore the initial velocity is going to be 0. Okay? And so as we toss it, it's going to move, and that's the downward trajectory that we've been talking about, okay? All right, so yesterday we were able to find then, and please make sure then that if you weren't able to get these answers here, please make sure you come by and see me. We were able to solve for the time. We used this particular kinematic equation right here. We used this one right here in order to solve for the time interval. Why? Because the initial velocity along the y we know is 0. We know the acceleration along the y is going to be negative 9.8 meters per second squared. And make sure you remember that the only acceleration that an object experiences as it's moving in this projectile manner is downward. Okay? And so that acceleration we know, and we're able to use the fourth equation here to solve for the time. And we solve for the time then as being 4 seconds. Okay? So it takes 4 seconds for the stone to fall from this elevated platform, from the cliff, the top of the cliff here, down to the surface of the earth. Okay? We were also able to solve then for the range. We were also able to solve for the range, that is the distance from the surface, from the cliff that the object falls, from start to finish, from x initial here. I'm sorry, x initial, not x final. From x initial, x final, So therefore, the range then we were able to solve for also yesterday because there's only one equation that we can use to solve for this one. And so please make sure you check that as well if you have any questions, which is going to be 20 meters. So we were able to discover then the range and the time interval of this particular motion. The last thing they asked for then, that they asked to solve for then, is the x and the y component, the x and y component of the velocity right before it hits the bottom here. Okay, so we want to find then, so we're also asked to find then the final velocity along the x, so we want to find that, and the final velocity along the y. So we want to find both of these as well. The first part should be pretty straightforward, folks, because if this is projectile motion, okay, so solving for the, when I say solve, we're not actually trying to solve for this at all, folks, because we know then this, sorry, along the x, we know then that when an object is moving in a projectile manner, which this stone is, the stone is moving in a projectile manner, we're looking at the downward trajectory, and that's what we're talking about. If we recognize that, then the final velocity here should be exactly the same as the initial velocity here, because there is no force acting along that stone along the horizontal. So therefore, there's no acceleration. So therefore, the velocity will be exactly the same. So there it is. We already have 1/2 of our solution there. So we've already solved for the x component. And when I say solve again, I put that in quotes because really we did not have to solve for it at all, as long as we recognize what the characteristics of an object is when it's falling in when it's moving in this manner here. Okay, which means then we have to solve then the only one we have to solve for then is v final along the y. Now going back to our kinematic equations here, we check our kinematic equations to see then which equation can give us v final. The very first one will give us v final right here. Okay, as long as we know what v initial is along the y, and we do, and that's going to be 0. As long as we know the acceleration along the y, which we do, it's right here. And as long as we know the displacement along the y, which we do, and it's right here. Okay, so therefore then we have everything we need to solve then for v final along the y if we want to use the first kinematic equation. So, but can we use that one? Sure, if we want to, but let's go through and see if we can find a simpler way to solve for v final. Let's take a look at the second equation. Second equation here gives us v final. Do we know what v initial is along the y? Yes, we do. Okay, so we have that. Do we know what the acceleration is along the y? Again, yes, we do, because it's negative 9.8. And then finally, do we have the time? We did. We solved for the time in the very first problem. Okay, we did that, so we have that as well. So this second equation will also give us the final velocity. The third equation here, will it give us final velocity? Well, yeah, it would, because there's final velocity right there. But we need displacement, and we have that. That's negative 78.4. We have v initial, we have it right there, which is 0. And then we have the time, which is right here, is 4. So any one of these equations will give us v final. Any one of those three will give us v final. Okay. Now, for me, it's up to you. Any one of those will work. But for me, it looks like the easiest one to use is going to be this middle one right here. So I'm going to go ahead. I'm going to use that middle one to solve then for v final along the y. So let's go ahead and write that down. So we know then that v initial is going to be 0. Okay, so it's going to be v initial along the y plus acceleration along the y times time. Okay, v initial is going to be 0. Okay, so therefore v final, the equation that can reduce then to v final is equal to acceleration along the y times time. And there it is. That's it. Let's go ahead then and substitute it in. Acceleration on the y is going to be negative 9.8 meters per second squared times the time interval of 4 seconds. Okay. And then we will get v final then as being negative 39.39. 39 meters. And that's what we have right there. And that's our answer. And so I think this is the easiest way to go about solving for v final along the y. And so please make sure then that you can work that out when it comes time. Okay, so if you have any questions on this, please make sure you stick around. You ask. I'll be available tomorrow after school as well, after my 7th period class. So please make sure you take advantage of that. Okay. All right. Let me go ahead then and let me save this here. And this here. And let me ask you on your paper. Okay. So grab a piece of paper right now. Let me save this. I'm gonna leave this up for you. Let's take a look, like I pointed out to you, I wanted us to do yesterday. Let's take a look at number 51 from your textbook. So it's on page 165. And what I'd like you to do then is on your paper, and make sure you submit it at the end of the period today. On your paper, I'd like you to do number 51 from the book. Take about 2 minutes to get this done, and then I'd like you to submit it at the end of the period today. Okay, so let's go ahead. Let's take 2 minutes to work out number 51 from page 165 in your book. Okay. Okay. Let's go ahead and let's take a look at this problem here. Let me go ahead and save this one more time. Let me clear this out, and let's use this screen here to help us work this out. Okay. All right. So in number 51, we have an object that's going to be thrown from the top of a cliff again. So again, drawing the pictures, folks. I know then that it seems a bit painful, a bit of a waste of our time, but drawing these pictures really help you to visualize what's going on here, folks. So let's go ahead then, let's draw our picture here. Okay, so there we have our cliff, our elevated platform. Here we have the surface of the earth. So let's go ahead and do that. So here is the surface of the earth. Okay. Here is our elevated platform or our cliff. We are told then that this cliff is elevated off the surface of the earth, and the distance is of 64 meters. Okay. It's 64 meters off the surface of the earth. Okay. We are told then that we have our object. Okay. And let's go ahead and draw that in. There's our object, and it is being tossed off the cliff, okay, off of our elevated platform here, with an initial velocity of 8 meters per second. Okay, that's everything we are told in this problem and nothing more. We don't need anything more. So let's go ahead then. Let's fill in the pieces of information that we are expected to know in order to solve for this problem. Okay, so let's start out then, first of all, with the acceleration. We know then that, and I'm sorry, the path that this object is going to take is going to be the downward part of the parabola. So it's going to take the downward trajectory. It's going to move in that manner there. Okay, so that's what we have. Okay. All right, so what do we know about this problem? Well, we know the acceleration along the y. The acceleration along the y is going to be negative 9.8 meters per second squared. Okay, so we know that. We also know then that if the velocity here is along the horizontal, we know then the initial velocity along the x is going to be 8 meters per second, whereas the velocity along the y will be 0 meters per second. So all of that we know moving forward with this problem. Also, I probably should include then that we also know then that the displacement, if the height of this cliff is 64 meters, the displacement in the downward direction, therefore the displacement, delta y here, we also know it's being negative 64 meters. So the very fact that they tell us that the cliff is 64 meters up above the surface of the earth, we know then that when the object falls, it's going to be moving a distance of 64 meters in the downward direction. Okay? All right, so that's all we have right there. So they ask us, first of all, to find the time. Okay, the time it takes to fall down to the surface of the earth here. So they ask us to find the time that it takes to fall down. And they are also asking us to find the range as well, how far away from the cliff it falls. And that means then that's the range, which is going to be our delta x. And that's what we're going to be solving for here as well. Okay, so make sure you keep that in mind. Let's go ahead then and let's solve for time. If we're going to solve for time, then we're going to use one of the kinematic equations. Let's go ahead and solve for that one first. Okay. So to solve then for time, and let's imagine this here. This equation, this first kinematic equation, we're not going to use because it doesn't even have time as a variable. So we're not going to use that one. Let's take a look at the second kinematic equation here. Okay. In order to solve for time, so they have the variable time here. In order to solve for time, we need to have the acceleration. And again, this is all along the vertical. So we're solving for the vertical motion here. Do we have acceleration along the y? Yes, we do. We have it right here. Do we have initial velocity along the y? Yes, we do. We have it right here. The only problem is we don't have the final velocity along the y. Could we solve for that? Yes. Once we solve for that, we can go ahead and use that equation to solve for time. Okay? But for right now, we don't have that either. Okay, so we don't have that. The third equation here, again, the problem again is that we don't have the final velocity. Okay? So with that said, it's going to be the fourth equation here. If you take a look at this fourth equation here, do we have all the components we need to solve for time? Yes, we do. There it is. There's time. We have the acceleration along the y, which is negative 9.8 meters per second squared. And we have the initial velocity along the y as well. And then we also have the displacement. So let's go ahead then and use this equation here to solve for time. Okay, so let's go ahead then. And remember, even though this is given to you as delta x, okay, we can write it in terms of y, which means that it's going to be delta y. It's going to be equal to v initial along the y times time plus 1/2 acceleration along the y times time squared. Okay. All right, so let's go ahead and work this out. We know that the initial velocity along the y is that's going to be 0. So this equation reduces then to displacement. It's going to be equal to 1/2 acceleration along the y times time squared, t squared. Okay. Solving for t then, and if you have an issue solving for t here, please make sure you come by and see me. Solving for t then, it's going to be 2 delta y all over a sub y. Okay. But at this point, then let's go ahead and plug in the numbers. Okay, making sure that you keep direction here, keep consistent with the directions. Delta y then is going to be negative 64 meters, folks. If you forget that negative sign, again, like I told you yesterday, you're going to get an imaginary number, which is going to make the answer a useless answer. It's going to be a nonsensical answer for us in terms of the physical universe. Okay, right. And then with that said, then the acceleration along the y then is going to be negative 9.8 meters per second squared. So plug that in. Right, so plugging that in, then we get our answer as being 3.6 seconds. Okay, so that's the amount of time it takes to fall down towards the ground. So we used the kinematic equation in order to solve for that one. Okay, I think then solving for the second part of the equation, the problem becomes very simple. Okay, because remember, there's only one equation that we can use to solve then for the range here, or for the motion along the horizontal. Okay, and that's going to be then delta x. It's going to be equal to v initial along the x times time. And this is the reason why we need to solve for time first. Okay, so let's go ahead then and let's plug that in. V initial along the x then is going to be 8 meters per second. Okay. Times the time, which we solved for here, which is going to be 3.6 seconds. Okay. So you plug that in, you get your answer then as being, I get here 29 meters as our final answer. Okay. Okay. So, let me go and do this really quickly. Sorry, you guys. Okay. So please make sure you can work through problems like this here. So this is the second type of projectile motion problem that you're going to see. The first type of problem then is going to involve then an object that is being shot up into the air and away. So it's going to move in a parabolic manner, so it's going to be up and away. The second type of projectile motion problem is the one that you see here. The object is going to be thrown off the cliff. Now, like I pointed out to you yesterday, an equally valid problem then is going to be one where you will have an object that starts down at the bottom, at the base of the cliff here. Okay. So you have an object at the base of the cliff here. And what we do in this case then is we're going to take this object and throw it up to the top of the cliff. Okay. So we're going to look at the upward trajectory, which means then what we're going to have is that we will have in this type of problem here, we will have then the initial velocity, and that initial velocity will be up and at an angle. So we need then to solve then for the x and y component of this velocity. So you got to keep that in mind. So in this case here, that we actually have to solve for the x and y component of the initial velocity. Whereas in the case where the object is being thrown off the cliff, we know what the x and y components are. Here, we can just use basic trig to solve then for the x component, x component, and the y component of this initial velocity. Okay? Because we know what will happen when we get up here. As we get up here then, the y component will be 0, and the x component then is simply going to be what we started out in the initial. Now that's the assumption we're making here then, is that it reaches the top of its height and then it stops, okay? and it falls on that ledge. Okay? Because if it doesn't, then we still have to solve then for the velocity along the y and velocity along the x. A little bit more involved, but it's still absolutely doable. Okay, so be prepared and be able to work through either type of problem where we're throwing an object off a platform, an elevated platform, or we're going to be taking an object throwing up to the elevated platform, and be able to work through those problems. And I think there was a couple of problems in your homework that reversed the process, and you had to we're looking at the upward trajectory rather than the downward trajectory. But either way, working through either type of problem, it's going to be exactly the same. All we're doing is kind of reversing things around a little bit. Okay. All right. So please make sure then that you take a look at those problems and work through them, and come by and see me if you have any questions involving this. Okay. All right. Very good. Let me go ahead then and let me save this here. Okay. Save it. Okay. Because what I'd like to do now then is that's it. That is, we are done with projectile motion. Okay? And so let me go ahead then and let's review really quickly what we've accomplished, what we've learned about projectile motion. Okay? So we said then that an object, okay, that is thrown, let's see, is the ground. Okay? An object then that is thrown from the ground, okay, it moves up, and then it comes back down. That parabola then, an object moving in that manner then is moving in 2 dimensions at the same time. Okay, it's moving, and we talked about this, and let's just stick strictly to the velocity. Okay? It's moving in the upward direction and the forward. It's moving sideways and upward at the same time. Okay? So therefore, there are 2 components of the motion here. And if we take a look at this, so if we look at simply, focus simply on the initial velocity, there is going to be then a vertical component and a horizontal component to it as well. Okay, so in this particular type of motion, then we have an object moving in 2 directions at the same time. So we have then the initial along the x and the initial along the y. Okay. And that's what we have right there. And at any point along the pathway here, we can define then, and let's make sure you keep this in mind, at any point along the path, let's say at this point here, and that's the velocity at that point. Okay? At any point along this pathway here, we can see then that the object is moving both horizontally, okay, and vertically at the same time. So at this point here, if we take a look at this point here, rather than at the initial point right here, we have that an object that's moving along the horizontal and the vertical at the same time. And this is going to be true at any point along that pathway. Okay? Now, if you understood that about projectile motion problems, you can imagine then, let's say then that we took this, so if you look at this, this looks like it's a half circle right here. Okay? Let's imagine that an object, if we extend it and we move it in completely in a circular manner, and that's a bad circle right there, but I'm sorry. But let's imagine then that instead of you throwing an object, okay, letting it go, you take the object, okay, and you anchor it to the center point here. So let's say then that, you take the object at the center point, and let's say then let's say you took a rubber stopper or some object, okay, an eraser, okay, and you tie it to a string and you swing it around, okay, and you swing it around yourself. And so if you notice then, as it is being swung around in a circle here, you see that it cuts out two pathways that look like they're parabolic in nature. Okay? And if you take a look at each point, if you look at each point along the pathway, whoops, sorry. If you take a look at each point along the pathway, okay, you're going to notice then that at each point, okay, the object is going to have then so let's go ahead and take a look at this point below the circle. Okay. This object then will have an X and a Y component as well. Okay, so horizontal and vertical component. So there it is. At this point as well, you have then a horizontal and a vertical. At this point in, as it returns back to the starting point here, we have then the velocity, if it follows that pathway there, we're going to have a vertical and a horizontal component as well. So any object moving in a circular manner, okay, so any object moving in a circular manner is also moving in a two-dimensional manner. So this is two-dimensional motion as well. Okay, so an object there's two ways that we can describe how an object moves in a two-dimensional manner. We can talk about projectile motion, and that's what we've dealt with so far. A projectile moves in a circular manner, I'm sorry, in a two-dimensional manner, but any object moving in a circular manner is also moving in two dimensions at the same time. Okay, and I hope I've illustrated that point here for you pretty clearly as well. And what we're going to do then is we're going to turn our attention now to exactly this type of motion here, the circular motion as well. So let's go ahead then and let's take a look at that. Okay. Right. Okay. So circular motion is also a specific type of two-dimensional motion that we're going to talk about here. But what we're going to do then is, because it's circular motion, we really can't use the descriptions that we've been using that describes an object moving in a straight line, in a linear manner. Okay? And so what we're going to do here then is that we're going to assign terms that are equivalent to what we've been using for velocity, for acceleration, and for displacement. Okay? But this time though, use that to describe then an object that is moving in a circular manner. Okay? And so we'll be talking about what's called angular speed, angular acceleration, and then the angular, and then I'll throw into that discussion also centripetal acceleration as well. And we're going to discuss all of those each in turn as we discuss circular motion. Okay? So an object moving in a circular manner is moving in a two-dimensional manner. It's moving in two directions at the same time. Okay? The only difference between projectile motion, one of the main differences between an object moving in a projectile manner and an object moving in a circular manner is that with the projectile motion, the object starts out at one location and ends up at another location. That was our range that we talked about. With an object moving in a circular manner, where it starts out and ends up at the same point. And that you need to make sure you understand. So the overall displacement ends up being zero. So what we're going to do then is we're going to talk about the displacement as we move along. Okay. And so as we talk about the displacement here, you're going to notice then that instead of talking about a straight line motion, we're going to actually talk about an arc in the motion here as well. Okay. And so what we're going to do then is when we talk about the displacement of an object moving in a circular manner here, we can't talk about it in terms of linear motion, because if that were the case, at any point, when you move the object, it always ends up where it starts out at. And so the overall displacement is going to be zero. So what we're going to do then instead is we're going to talk about the displacement in terms of an arc that it sweeps out. Okay? And that arc then we can use this and we can assume that it's going to be a straight line. We can approximate that arc with a straight line, but make sure you understand that that straight line is only an approximation as we go through this. Okay. All right. So with that said, then we can also describe then acceleration. Now, why is that? Why does an object move in a circular manner? How can we say that it accelerates? Well, let's go back to what we said with the projectile motion. The acceleration, there's only one acceleration, and that acceleration is due to gravity. Okay? There is no gravity could be one of the forces acting on an object moving in a circular manner. Okay? But you have to understand then that the object is constantly undergoing acceleration. We'll talk about the forces a little bit later. We'll talk about what forces are acting on this object as it moves in a circular manner. But the object does accelerate. How do we know that the object is accelerating? It can be moving at the same speed. Now, if you change its speed, yes, that's obviously accelerating because it's increasing its speed. If you slow it down, it is accelerating because it's changing its speed. But remember, we said that acceleration also involves a change in direction. So the reason why an object moves in a circular manner is constantly accelerating, even though it is moving at a constant speed. Let me make sure you understand this. An object moving in a circular manner, an object spinning in a circle, is constantly accelerating, even if it's moving at the same speed. Even if its speed is constant. Why? It's changing direction constantly. It's always changing direction. And at any point, it's always changing its direction. As a result of that, then, the object is undergoing acceleration. Now, we refer to that acceleration that is as centripetal acceleration, and that is an acceleration towards the center. Okay? The reason why the acceleration is towards the center of the circle, so if you can imagine what we have here and what I've pointed out to you here, okay? If you can imagine this, then you look at the acceleration vectors here, each one of those acceleration arrows then is pointing towards the center. And we can do simple math to show that that will be the case. But the reason why the acceleration is pointing towards the center is because that's where the force is. The force that is causing the object to turn in that circular, that's causing the acceleration, is also towards the center. So the only force acting on this object, and again, we're going to ignore air resistance, we're going to ignore everything else. The only force acting on this object will also be pointing towards the center. Okay? So what that force is, we will talk about, and I'm running out of time here, but what that force is, we will talk about once we get back from break, okay? But understand this, that there is one overall force acting on this object here, and that's what we refer to as the centripetal force. Okay? That centripetal force is not an actual force in nature. It's one of the forces in nature that's keeping the object spinning in a circular manner. And that's why, if you notice here, the acceleration vectors here are all pointing towards the center. And again, if you like, we can show this by adding these vectors, velocity vectors together, that the direction of this acceleration is always going to be towards the center. At any point along this circular pathway, the acceleration will always be pointed towards the center. So you want to make sure you keep that in mind. So we call that acceleration then centripetal acceleration. That is the acceleration towards the center of this circular motion here. Okay. All right. Let's go ahead then and let me just show you really quickly here. Whoops, sorry. Okay. Okay. So if you notice here, you add the vectors together, the change in velocity is going to be towards the center. And so that like I said, change in velocity over time, that's your acceleration, and that acceleration is always going to be towards the center. So therefore, centripetal means then center seeking. Okay? Now, we can find that acceleration. We can calculate for that centripetal acceleration if we know a couple things here. Okay? If we know the velocity, if we know the linear velocity, and we'll talk about we'll talk angular velocity, angular acceleration. We'll talk about that a little bit more in chapter 8. I'm sorry, in chapter 8 here, we'll talk about that. But what we're going to do then is we're going to focus in on this straight line motion. I'm sorry, chapter 7. Okay. We're going to focus in on the linear motion here. So this velocity here, if we take a look at this, that's the linear velocity that we can trace along this pathway here. The way that I try to get you to imagine this, and for those of you who will be here, there's going to be a simple centripetal acceleration lab that I'd like us to do. For those of you at home, there's a really simple setup that we're going to you can use as well. I'll have that lab posted for us. So our next lab is going to be an actual physical lab. I'll post that lab for us when we get back from break. But you're going to be able to see then that this object does have two types of velocities. It does have a linear velocity, but it also has a circular angular velocity as well. Again, we'll talk about the angular velocity in chapter 7. But what does this linear velocity look like? How could you imagine what this linear velocity is? Well, if you take an object and you spin it around, you tie it to a string, like I said, the eraser, and then you spin it around. If you let go of the string, the object stops spinning. That eraser stops spinning in a circle. And what does it do? It moves in a straight line manner. And so what I would like to do, and I'm sorry, I'm running out of time, or what I'd like us to do then is when we get back from break, I'm going to review this with you, and we're going to focus our attention then on this linear velocity here. Okay. All right, folks, have a good break. I hope that you're able to stay safe. I hope you're able to enjoy your time away from school. And I will see you folks back here after the break. Okay. All right. Have a good vacation, folks. And I will, I'm sorry, what am I thinking? I'll see you folks tomorrow for the stations in the cross. Okay. So I'm sorry, I'll see you folks tomorrow. Okay. All right. I'll see you tomorrow, folks. Bye.